Hello, today we will be studying quantum numbers. Quantum numbers are used in chemistry to describe the motion of an electron in an atom. In fact, the motion of electrons is possible with the description of a variety of quantum numbers. But in chemistry, practically apply exactly 4 quantum numbers, which we will talk about today. These numbers are denoted by letters. N is the principal quantum number. L is the orbital quantum number, as well as ML is the magnetic quantum number, and MS is the spin magnetic number. Let's figure out where these letters, respectively numbers, come from, and find out what meaning they have in relation to the electron. That is, what characteristic of the electron these quantum numbers have. So let's start with the main quantum number. The main quantum number itself was introduced due to the Schrödinger equation. You can see this equation here. In this equation, there's the mass of the electron. There's a tab here, which is the charge of the electron, of course, the pi number, as well as the frequency constant and the principal quantum number. You can see it here. We can simplify this formula and write a shorter version of it, where K would be an expression that deals with everything except this number N. Now let's find out what this prime quantum number means. So N, this number shows how many levels there will be. Or we can say it's going to be levels or layers, respectively. Sometimes it's said that way. This number can only take integer values. It can be 1, 2, 3, and so on up to infinity. But at present in the periodic system, there is a maximum principal quantum number equal to 7. According to the 7th ordinal number of the level, which you can see in the periodic table. Now, knowing the principal quantum number, you can determine not only in which respectively level the electrons of a given element are located, but you can also calculate how many electrons will be in a given energy level. There is a formula by which you can make such a calculation. This formula looks like this. N is large equals 2n squared. Now, if we substitute n for each of the levels, for example, if n is equal to 1, then the maximum number of electrons for that energy level would be the 2. This is why only 2 electrons can fit on the first level at most. Accordingly, we can calculate this for the second, for the third, and so on. The maximum number of electrons is calculated using this formula. For this formula, we need to know the principal quantum number. Now, the next number is called the orbital quantum number. It's a rather complicated concept that's related to a vector quantity called L, which in turn is related to the orbital number, which is denoted by the letter L. This is the location of the electron in space, and it is related to the orbital momentum of the electron. Or, to put it simply, it's the shape of the orbital that a given electron will take. We can express it either by this formula or by the formula squared. And L is our orbital quantum number. L itself is related to the principal quantum number by the formula N1. So if N is equal to 1, then the orbital number takes the value 0. The value 0 has electrons, which we denote by the letter S. These are the electrons that a spherical electron cloud has. Now, if N is equal to 2, then the orbital number L takes the previous value of 0 at the beginning and corresponds to the S orbital. And then an L equal to 1 is added. This corresponds to the p orbital, which has the shape of a volume 8, and so on. If we do this for the third level, there will be L equal to 0. L will be equal to 1, and a new L equal to 2 will be added, which corresponds to the d electrons. Once again, s electrons have a spherical shape. P electrons have the shape of a volume 8, and d electrons have a complex electron shape, well, for example, looking like two 8s connected together. So the orbital number allows you to predict what the shape of the orbital will be. It is described either through the number or the shape labeled S, P, D, and F. Next, the magnetic quantum number. This number in turn is related to the way an electron moves in a magnetic field. It is also a related number, usually with a projection on the z-axis, in which case we can see formulas also related to quantities that are also in the orbital and respectively the principal number. The magnetic number allows us to predict how the electron is distributed additionally still in quantum cells. In turn, this ml value takes the value plus or minus L, with the value passing necessarily through 0. So if we have L equal to 0, then ml will also take the value 0. Further, if ml is 0 respectively, it will be 0 for the s electron of the second level. And for example, the ml for the p electron will be minus 1, 0, and plus 1. And so on for all the other electrons, which we can see are different in terms of orbital quantum number. But I should say that there is a projection of this number that we can represent as quantum cells. For example, then we need to know that the number of quantum cells is calculated by the formula 2L plus 1. And then if the magnetic number is ml0 and the orbital number is 0, then the number of cells will be 1. This corresponds to the s electrons. That's why s electrons are placed in one quantum cell. If they are p electrons, then the number of cells will be 3, respectively. Well, and if we are talking about d electrons, then in this case the number of cells will be equal to 5. The number of quantum cells will always be odd, 1, 3, 5, and the maximum at the moment is 7. Well, now we come to the spin magnetic number. The spin of an electron is a special motion of an electron. In general, it is difficult to find any analogy to its motion, but sometimes they say that the electron moves like a wave. Hence the name of this number, spin, spinning like a wolf. But in fact, this concept is more complicated, and it is also related to a certain angular momentum that the electron has. As you can see, its formula is also related to a constant number. And this number is related, the spin number is shown here by ms. But ms can take the value of the spin number, and it's not related to the other numbers that we showed earlier. It can only take the value of either plus 1, 2. This corresponds, if we're talking about quantum cells, to the position of the arrow. The electron is shown by the arrow position up. If the spin number takes a value of minus 1, 2, then the electron in that cell is indicated by a down arrow. But then the given characteristics that we have just gone over with you allow us to describe how the electron moves. In this case, the atom is considered as hydrogen-like. That is, from the point of view of the hydrogen atom, these concepts are introduced. Using these numbers, we can explain what electrons are distributed in an element, where they will be located, and what set of quantum numbers will describe them. In the next lesson, we'll try these exercises to make it clearer. Goodbye.